Join us for an in-depth exploration of Michael Faraday's revolutionary discoveries in electromagnetic induction that transformed our understanding of electricity and magnetism. In 1831, Michael Faraday discovered electromagnetic induction, showing that moving magnets near coils of wire could generate electricity, a finding that would revolutionize science and technology. To appreciate Faraday's breakthrough, we must understand the state of electrical science in the early 19th century. By 1820, Hans Christian Ørsted had shown that electric currents could deflect compass needles, proving that electricity creates magnetic effects. André-Marie Ampère then demonstrated that current-carrying wires experience forces in magnetic fields and can attract or repel each other. Scientists knew electricity could produce magnetism, but the reverse process remained mysterious. Could magnetism produce electricity? This was the burning question. The central question that captivated scientists was whether the reverse process was possible. Could magnetism somehow produce electricity? Michael Faraday brought a unique perspective to this problem, shaped by his humble origins and experimental genius. Michael Faraday was born in 1791 in London, the son of a blacksmith, with little formal education. He educated himself by reading scientific books while working as a bookbinder's apprentice, developing a deep fascination with natural philosophy. Faraday's approach combined careful reading of scientific literature with meticulous experimental investigation, believing that nature's secrets could be revealed through systematic observation. In 1813, he became laboratory assistant to the famous chemist Humphry Davy at the Royal Institution, where he would spend his entire career. Let me describe Faraday's crucial experiment of August 29, 1831, which changed everything. Faraday wound two separate coils of wire on opposite sides of a soft iron ring, one connected to a battery, the other to a galvanometer. Here's a diagram of the iron ring with two coils. The primary coil in red connects to a battery, while the secondary coil in blue connects to a sensitive galvanometer for detecting current. Faraday expected that a steady current in the first coil would produce a steady magnetic field, which might induce a steady current in the second coil. But he observed something completely unexpected. The galvanometer showed current only at the moments when he connected or disconnected the battery, not during steady operation. This graph shows the dramatic result. The red line shows steady primary current, but the blue arrows show induced current spikes only when the primary current changes, not when it's steady. This was revolutionary. Only changing magnetic conditions produce electric effects. Static magnetism, no matter how strong, produces nothing. Faraday then performed a series of elegant experiments with moving magnets that revealed the fundamental principle. When Faraday pushed a bar magnet into a coil of wire, the galvanometer deflected in one direction, showing induced current. When he pulled the same magnet out, the galvanometer deflected in the opposite direction, showing current in the reverse direction. Here's the setup. A bar magnet approaching a coil. As the magnet moves toward the coil, magnetic flux through the coil increases, inducing a current that the galvanometer detects. Crucially, when Faraday held the magnet stationary inside the coil, no matter how strong the magnetic field, the galvanometer showed zero current. Faraday also observed that faster motion of the magnet produced larger deflections, indicating that the rate of change mattered, not just the change its. To understand Faraday's law mathematically, we must first define magnetic flux, a concept Faraday himself introduced. Magnetic flux is a measure of the total magnetic field passing through a given surface area, quantifying the magnetic influence through that region. Mathematically, magnetic flux phi b equals the surface integral of the magnetic field B, dotted with the area element dA. For a uniform magnetic field, this simplifies to phi b equals b times a times cosine theta, where theta is the angle between field and surface normal. The SI unit of magnetic flux is the Weber, where 1 Weber equals 1 Tesla times 1 square meter, or equivalently 1 volt second. This diagram shows magnetic field lines passing through a surface. The flux is the product of field strength, area, and the cosine of the angle between them. Faraday performed hundreds of careful measurements to establish the quantitative relationship between changing flux and induced voltage. Faraday systematically varied the number of turns in his coils, the strength of his magnets, and the speed of motion to see how each factor affected the induced voltage. He measured induced voltage by carefully calibrating galvanometer deflection angles, establishing a quantitative scale for his observations. This graph shows Faraday's crucial discovery. The induced voltage is directly proportional to the rate of change of magnetic flux. The data points fall perfectly on a straight line through the origin. The key insight was that induced voltage is directly proportional to the rate at which magnetic flux changes, not to the flux itself or its absolute value. Let's now express Faraday's discovery as a precise mathematical law, one of Maxwell's fundamental equations. Faraday's law states that the induced electromotive force equals negative d phi b dt, the negative rate of change of magnetic flux. The negative sign, discovered by Heinrich Lenz, shows that induced currents always flow in a direction to oppose the change in flux that created them. For a coil with n turns, the induced EMF is multiplied by n, giving epsilon equals negative n d phi b dt, showing why more turns produce stronger effects. This elegant equation unifies all electromagnetic induction phenomena, from Faraday's ring experiment to modern electric generators and transformers. From this one fundamental law flow countless applications: electric generators that power civilization, transformers that distribute electricity efficiently, and wireless charging systems. Let's work through a concrete numerical example to see how Faraday's law works in practice. Consider a circular coil with radius 10 centimeters and 50 turns of wire. The area of the coil is pi r squared, which equals pi times 0.1 squared, or 0.0314 square meters. Suppose a magnetic field perpendicular to the coil increases uniformly from 0 to 0.5 Tesla in 0.2 seconds. The change in flux is final B times area minus initial B times area, which equals 0.5 times 0.0314, giving 0.0157 Webers. The rate of flux change is delta phi B over delta T, which equals 0.0157 divided by 0.2, giving 0.0785 Webers per second. The induced EMF is epsilon equals negative nd phi dt, which equals negative 50 times 0.0785, giving negative 3.93 volts. This calculation shows that about 4 volts are induced, which is enough voltage to light a small LED or power low-voltage electronic devices. Let's understand why Faraday's discovery contradicted the prevailing contact-based theories of electricity. Before 1831, the dominant theory held that electricity required direct physical contact between different substances, as in voltaic batteries. Contact theory held that electricity arose from direct contact between dissimilar metals, as shown in this diagram of two metals touching. But Faraday showed conclusively that electricity could be generated without any physical contact, merely by changing magnetic conditions through empty space. This forced scientists to accept action at a distance through invisible magnetic fields, a radical departure from mechanical contact-based thinking. Faraday introduced the revolutionary concept of fields as physical entities that permeate space and transmit forces. Faraday proposed that electric and magnetic fields exist as real physical entities throughout space, even in the vacuum of empty space. This shows field lines, Faraday's visualization tool. The arrows represent the direction of force that a charge would experience, with density indicating field strength. Faraday recognized that fields themselves carry energy and momentum, making them as physically real as matter is. The energy density in electromagnetic fields is 1/2 epsilon 0 E squared plus 1 over 2 mu 0 B squared, showing fields store real physical energy. Faraday identified 3 distinct ways to change magnetic flux through a coil, each producing induced voltage. First method: vary the strength of the magnetic field itself, as in Faraday's iron ring experiment when switching the battery on or off. Second method: change the area of the coil that's exposed to the field, such as by expanding or contracting the coil's dimensions. Third method: rotate the coil relative to the field direction, changing the angle theta, and thus the effective area perpendicular to the field. This shows 2 methods. Top panel shows changing field strength B, bottom shows rotating a coil to change the angle. Both change flux and induce voltage. Mathematically, d phi dt equals a dB dt plus b dA dt plus b a d cosine theta dt, showing all 3 contributions to flux change. Let's see how Faraday's discovery led directly to electric generators, the machines that power modern civilization. An electric generator works by continuously rotating a coil in a magnetic field, using method 3 to produce a constantly changing flux. Here's a simplified generator. A rectangular coil rotates between magnetic poles. As it spins, the flux through it varies sinusoidally, inducing alternating voltage. For a coil rotating at angular velocity omega, the flux varies as phi b equals Ba cosine omega t. Taking the time derivative gives induced EMF as epsilon equals negative NBA omega sine omega t, producing sinusoidal alternating current. The peak voltage is epsilon peak equals NBA omega, proportional to number of turns, field strength, area, and rotation speed. A typical power plant generator produces around 20,000 volts at 60 Hz frequency, spinning at 3,600 revolutions per minute. Transformers use Faraday's law to efficiently change voltage levels, enabling long-distance power transmission. In a transformer, alternating current in the primary coil creates a time-varying magnetic flux in a shared iron core. This changing flux passes through a secondary coil wound on the same core, inducing voltage according to Faraday's law. This shows a transformer with primary coil on the left, secondary on the right, both sharing a common iron core that efficiently channels magnetic flux between them. The transformer equation is V2 over V1 equals N2 over N1, showing output voltage is proportional to the ratio of turn numbers. A step-up transformer has more turns in the secondary than primary, increasing voltage for efficient long-distance transmission. A step-down transformer has fewer secondary turns, reducing voltage to safe levels for home and industrial use. Faraday's law also explains eddy currents, circulating currents induced in bulk conductors by changing magnetic fields. When flux changes through any conductor, not just coiled wires, circular currents called eddy currents are induced throughout the material. This shows eddy currents as circular patterns within a conductor. Blue arrows represent changing magnetic field entering from above, inducing these swirling currents. Eddy currents flowing through the conductor's resistance dissipate energy as heat, which can be problematic or useful depending on application. Applications include induction cooktops that heat metal pans, magnetic brakes in trains, and metal detectors at security checkpoints. Faraday's law leads to the important concepts of self-inductance and mutual inductance. Self-inductance occurs when a changing current in a coil induces voltage in that same coil, opposing the change in current. The self-induced EMF is epsilon equals negative LDI/dt, where L is the inductance measured in henries. Mutual inductance describes how changing current in one coil induces voltage in a nearby second coil, as in transformers. The mutually induced EMF is epsilon 2 equals negative MDI1dt, where M is the mutual inductance coefficient. Inductors are circuit elements that store energy in magnetic fields, playing crucial roles in filtering, timing, and energy storage applications. This diagram shows a coil with self-inductance. When current changes in the coil, it induces a voltage in itself due to its own magnetic field,